Statistics from home. Today, we're going to take a hard look at some very serious data about the coronavirus pandemic data coming from New York City. And specifically, we're going to look at some information that has been reported. I first saw it on April 8th about racial disparities in the fatality rates related to the COVID-19 disease. So I'm going to call your attention to this data that comes from health.newyork.gov, and particularly this data here. This is data about the race and ethnicity breakdown of people who have died from the coronavirus infection. Now, the first thing that might jump out at you here is that the percentages are different. There are different percentages of people in each racial ethnic category. So 28% of deaths are Black, 27% of deaths are white, only 7% of deaths are Asian, 34% of deaths are Hispanic, and 4% of deaths are other. So the differences between these figures in and of themselves is not surprising and doesn't even in and of itself represent an inequity. One wouldn't expect equal numbers of Asian and white and Black people to be dying from the COVID-19 infection because there are not equal proportions of Asian and white and Black people in the population in the first place. So the fact that these numbers are simply unequal is probably not surprising. What would we expect about the fatality rates among different racial ethnic categories from this disease? We would expect that it should be approximately proportional to the number of people in each category in the overall population. And what this data is actually calling our attention to is that it's not even equal to that. So for example, 22% of the population of New York City is Black. 28% of the deaths recently from the COVID-19 infection have been deaths of Black people. And so the inequality between these numbers is natural. The inequality between this 28% and this 22% is not natural and warrants some sort of investigation or some sort of explanation is appropriate here. Although whites make up 32% of the population, they only make up 27% of the COVID-19 fatalities. And so this is strange and surprising. So what we're going to do is we're going to use this data to study some of the ways that we make deductions about proportions, about significance levels of differences between two proportions, and how we make more sophisticated tests that can detect whether this information is really statistically significant or whether this is possibly just due to chance. So the first question that we're going to focus our attention on is this question about these Hispanic numbers. Let me recap what these mean. This 29% of the population means in New York City, approximately 29% of the population identifies as Hispanic. This 34% is a percentage of fatalities. It means that among COVID-19 fatalities, about 34% of those fatalities are among people who identify as Hispanic. Now, that sounds like a pretty big difference. It's not quite obvious from looking at this what the sample size is. And so that's something that we need to sort out. Is the difference significant? That's going to be our first question. And we're going to run a hypothesis test to see whether the difference is significant. Now, I want to remind you right away that when I say significant, I mean statistically significant. Every death is significant and important and very, very relevant to us in terms of social policy. So there is a difference here between the statistical sense of the word significant and the more natural sense of the word important. Okay, so of course, this is important. The question is, do we find statistical significance in a mathematical sense here? So what we're going to do is we're going to test these, this proportion measured 34% versus an anticipated value that would be 29%. I transcribed some of this data to a Google spreadsheet, and I had to do some calculations because this doesn't actually make it very obvious what are the sample sizes. And so I had to do some calculation of the sample size. This is New York City. I'm approximating that New York City means the sum of the 5 boroughs. And so I'm calculating the fatalities in the 5 boroughs here and getting a sample size of 9,708, which is horrifying. And that's the number of fatalities as of April 19th in the 5 boroughs. So on the basis of that information, we can calculate the observed count of fatalities among Hispanic people and the predicted count of fatalities among Hispanic people that is predicted if there had been 9,708 fatalities. So how do we do that? We take the proportion observed, which is 34%, and multiply it by the sample size to get 3301. This is, to within rounding error, this is our best guess at the number of Hispanic fatalities that are actually reported. This 2815 is the number of Hispanic fatalities that would have been reported if 29% only of the fatalities had been among Hispanics. That's a smaller number, obviously, because 29% is smaller than 34%. So this is the actual measured value here, and the actual value of n is going to be 9,708. So we want to run a hypothesis test. The first thing that we need to clarify is what are our hypotheses. Our alternative hypothesis is that the proportion of Hispanic people, the proportion of those fatalities which are Hispanic would be 29% of all fatalities. The null hypothesis would be greater than 29%. The null hypothesis is a statement that it would be equal to 29%. So here we basically mean among all potential fatalities, all future or potential fatalities coming from this disease. The null hypothesis asserts that that's equal to 29%, and the alternative hypothesis states that it's greater than 29%. For the null hypothesis to be true, this disparity between 34% and 29% has to be coming from pure coincidence. It has to be just the luck of the draw, perhaps because the sample size is not large enough to give us an accurate measure yet. Now, if that seems implausible, it's because it is implausible, but we need to run the hypothesis test so that we can see how plausible that is. So let's think about our null story. The null story states that Hispanic people in New York are equally likely to die of COVID-19 as anyone else. And so we should expect a 29% fatality rate, 29% of fatalities to be Hispanic. We would naturally expect some variability due to random chance, and that's what's explained by standard error. And the deviation, the 5% deviation from that we're actually seeing in the measured data is explained by coincidence. That is the null story here. Now, is it plausible or not? That's what the hypothesis test is meant to assess for us. So what are we going to do? We're going to calculate on the basis of the data. We're going to find the standard error. We're going to calculate the z-score, and then we're going to calculate the p-value from the z-score using some sort of CDF tool. So that's what we're up against here. Now we're going to do all of these calculations within this Jupyter notebook. So let's see how that's going to go. So we're going to copy the measured value of p, the anticipated value of p given by the null hypothesis, and we're going to copy the measured value of p hat given by the actual data. Then we're going to calculate the sample size n, which is going to work out to be 9,708. That's calculated here from this data. So we're reading in the data here. So we're calculating the n, now we're calculating the standard error. The standard error is calculated by this formula, which is also given here in a prettier format, the square root of p times 1 minus p over n. When we calculate the standard error, we have to plug in n, which is this value n, which is about 9,000. We also have to plug in the value p. Now, it's not always obvious which value of p we should plug in. We actually have two different values of p here to plug in. Which one is correct? The 29% is correct. The value marked p, not p hat. Why? Because the null hypothesis explains to us that the correct value of that proportion is actually 0.29, and everything else is due to random variability. So if the correct value is actually 29%, that's what we should plug in. This is, again, all hypothetically as if the null hypothesis were correct. So we're going to plug that p-value in here to get the standard error. And then the formula for the z-score will be the usual formula for the z-score. The measured value, which is p hat, take away the anticipated value, which is p, and divide by the standard error. Now, if we look down here, we can see the actual calculated values for all of these things. The sample size is 9,708. The standard error is 0.0046. This is a very small value for the standard error. It's less than half of 1%. And the reason that it's so small is because the sample size is actually very large. And so we should expect quite a lot of accuracy here. Because the standard error is small, the z-score that we get is, well, that might not look like an enormous number, but for a z-score, having a z-score higher than 10 is an enormous, overwhelmingly strong z-score. And the p-value that we get is ridiculously tiny. So let's figure out what that means. First of all, I should point out that the way we usually get the p-value from the z-score is using some sort of online tool. I might plug in 10.86 here to figure out the p-value. This tool is limited to a range of values for the z-score between -4 and 4, because these are the usual values for the z-score. A z-score like 10.86 is a ridiculously large z-score, which means that this tool can't really calculate that, and it's going to give us 0. 0 is approximately the right answer. In order to get the right answer with more precision, we need to use this norm.cdf function, and that will give us the true p-value, which is this absurdly tiny number, 9.264 times 10 to the lots, 10 to the minus a very large number here. So this is an absurdly small p-value. What does that mean? That means that it is far, far less than any reasonable threshold of significance, right? 0.05 would be here, right? We would have a 5 here. It's way, way, way less than any alpha that anybody would reasonably have. And that means that the null hypothesis is just is utterly rejected here. The null hypothesis has no more credibility. So our conclusion here, the test statistic is enormous. The p-value is microscopic. So with a vengeance, we reject the null hypothesis and we conclude that p is greater than 0.29. That is, there is a statistically significant difference. What does this really mean in practice? It means that this difference is real. What this data is showing us, 34% compared to 29%, with a sample size of about 9,000, what this data is showing us is it is showing us a real effect among this population. Something is happening here. This is not merely the result of the random chance, the luck of the draw, the randomness of this sampling. Something else is happening. So unfortunately, it doesn't tell us what is happening, right? If you report this to any politician and say, you know, there is a real effect here, Hispanics are dying faster than others of this disease, then the only sensible response is, well, then why and what do we do about it? This test for significance tells us that the effect is real, but it doesn't tell us why, and it doesn't tell us what to do about it. And so that's a really important thing to understand. There are, of course, limitations to the statistics. The statistics can measure the effect. The statistics can distinguish a real effect from a completely random coincidental effect, but they're not magical. They can't tell us what's the real reason behind this, and they can't tell us what we really ought to do about it. They just tell us that the effect is real. So this has been a hypothesis test in which we've compared a single proportion against a fixed value, and we've come back rejecting the null hypothesis here. In the next test, I want to compare black and white fatalities. The reason for this is because this gives us an opportunity to compare one proportion to another, which is a different structure of a hypothesis test, and it's important for us to be able to do that too. So here we're going to focus on the rows labeled black and white, and we're going to compare these ratios to each other. So here's our first attempt here. What we're going to do is we're going to say, oh, okay, the proportion reported for blacks is 28%, and the proportion reported for whites is 27%. And we're going to compare them against each other. So we're going to compare an alternative hypothesis, P1, I think that's the proportion for blacks, is greater than P2, that's the proportion for whites. And then that could be translated to say that the difference between them is positive. And then the null hypothesis will say, no, P1 is equal to P2. Fatalities are equally likely to be black versus white. However, I mean, this is like a reasonable first attempt for getting started on this problem, but this setup actually doesn't make a lot of sense. I mean, it is possible to run the hypothesis test this way, but this setup is really just not very sensible. It's poorly considered. The reason is because it is not reasonable to expect that these numbers should be equal in the first place. The reasonable expectation is not that the percentage of deaths that are black deaths and the percentage of deaths that are white deaths should be equal to each other. That's not what would be reasonable to expect if things were equal, if there were no effect. What's reasonable to expect is that they would be in proportion to the rest of the population. So in other words, the reasonable expectation is not that these numbers would be equal to each other. The reasonable expectation, if there were no bearing to race or ethnicity in this whole conversation, would be that they would be in proportion to how much of the population they make. And so this is really not a very well considered hypothesis and doesn't really inform us the way we want to be informed. So instead of considering the percentage of fatalities which are black and the percentage of fatalities which are white, we want to turn this around and we want to consider the proportion of black people who have died and the proportion of white people who have died. So these are completely different numbers. Basically, what we're trying to measure here is what is the overall mortality rate of all black New York City residents deriving simply from COVID-19? And then what is the overall mortality rate of white New York City residents attributable to COVID-19? So the same question. Now, these are going to be much, much smaller proportions, but we can still work with them. I say they're going to be smaller proportions because now we're measuring this out of a proportion of all white people or all black people in New York City. So we're measuring thousands out of the millions of residents all total. So they're going to be much smaller proportions, but these are the right proportions to measure because this really reflects the mortality rate and the level of danger to each population. So we're going to have to work on calculating them, but let's just imagine that we can calculate these, the overall mortality rate to black people and the overall mortality rate to white people. Let's assume we can calculate them. Now, the alternative hypothesis should be phrased this way. In New York City, blacks are more likely than whites to die of COVID-19. That is, the probability of death is higher in one population than in the other. And we would get this inequality this way. P sub B is greater than P sub W, or if we subtract P sub W from both sides, P sub B minus P sub W is greater than 0. And then the null hypothesis, which corresponds to this, is this statement that P sub B minus P sub W is equal to 0. In other words, this states that P sub B equals P sub W, right? If you just add P sub W to both sides. So this is the null hypothesis is the statement that COVID-19, at least so far as fatalities are concerned, is equally dangerous to whites and to blacks. That's basically the content of this null hypothesis. So we need to understand what the null story really entails before we can know how to assess whether it's plausible. The null story says that in New York City, blacks and whites are in fact equally likely. Likely to what? Likely to die of COVID-19. It tells us that we ought to expect equal mortality rates here. And it also tells us that we should expect some variability due to random chance. And this variability due to random chance comes from standard error. It's just the luck of the draw, just coincidence, right? We should expect some variability. And so just because we measure this and we get something non-zero, that doesn't by itself mean that we've proven the null hypothesis false. We should expect some variability due to random chance. We need to be able to measure and assess how much variability we expect to get, and that'll be the standard error for the difference. So if the deviations from 0% are explained by coincidence, then they are attributable to the standard error of the difference of two proportions. And so what we're going to do is we're going to calculate the standard error and the z. Now the standard error formula is going to be a combination of two different formulas. The first formula is the one that we used before, namely the standard error is the square root of p times 1 minus p over n. That's going to be the first formula for the standard error that we're going to need to use. But because in this problem we're calculating the standard error for a difference, then we need to use that formula once and use that formula twice, and then square the results and add them and take the square root. So here we have this Pythagorean combination, the square root of the sum of the squares of the individual standard errors. And I combine them this way because it gives you an opportunity to see an interesting little cancellation here. We have a square root here, but then it's immediately followed by a square. And we can cancel that to just simplify to this and simplify to this. Notice here that this is going to be p hat sub b. That is the measured mortality rate in the population of people, which is the black people. And then this will be the population of people, which is the white people. So this is the measured mortality rate among white people. This is the measured mortality rate among black people. This is the sample size among black people and the sample size among white people here. So here, this is how these things need to get combined. Now, I would love to have p instead of p hat, but p hat is the only thing that I see. And so I cannot actually plug in the value p because I don't know the true value p. I just have to plug in the measured value p hat. What formula will we use for the z-score? The same formula we always use, the measured minus the observed over the standard error. And applying this formula is a little bit tricky and we need to be careful. So what are we measuring here? The alternative hypothesis says this difference should be positive. The null hypothesis says this difference should be negative. And the standard error is the standard error for the difference. The measured value is the measured value of the difference, which is the measured difference here. The observed value is the predicted value of the difference. And so here, the measured value is actually the measured difference. It's this term in this equation. I wrote measured minus observed. That should be measured minus predicted. So let me change that. The value that we subtract should be the predicted value here, which is the 0 predicted from the null hypothesis here. So that's minus 0. And then the standard error will be whatever we calculate the standard error to be. So finally, after we have the z-score, then we can deduce p from the z-score using any ordinary tool. We could use this tool, or we could just use the Colab functionality itself. So this is the plan of approach here. We're going to try to measure the difference between these two proportions. We need to begin with actually measuring these proportions, which is a little bit tricky because we're not actually given the overall mortality rates of each population here. So the first thing we need to be concerned with is how do we actually measure the overall mortality rates from this data? Well, this data tells us how many fatalities there are among the blacks and among the whites. We can use public data to figure out the population. And then this data also tells us which percentage of the population, what percent of the population is black or white. And so we compare that together with public information about the total population to figure out what is the overall mortality rate. So that's what I'm computing here. And let's step through the calculation carefully so that we're sure that we understand it. So first we'll get the total population of New York City. And then we'll take 22% of it for the population which is black, and 32% of it for the population which is white. And I'm getting those figures from here. Then we'll calculate the fatalities. This is the number of black fatalities, and this is the number of white fatalities reported. Then finally, we can take the fatalities divided by the total population size to calculate the fatality rate or the mortality rate. And it has a subscript, it's p hat, right? And it has a subscript b because that's for the black population, and then p hat for the subscript w because that's for the white population. So in each case, we managed to calculate the number of fatalities and the total size of that population, and then we get a mortality rate for each population. Now, this looks a fright here, but this is nothing more than this calculation here for the standard error with everything plugged in. So I'm basically just taking this formula and plugging everything in, and that's gonna tell us the standard error, okay? So for now, ignore these two lines. We'll return to those in a few minutes. Now, the z-score, that's just this formula with the standard error plugged in, and then we have the results here. So it turns out that so far, the mortality rates have been 0.147% and about 0.1%. So this is the overall mortality rate among blacks in New York City of the disease COVID-19. And then this is the overall mortality rate among whites in New York City from COVID-19. Then we get a standard error. That's the standard error for the difference because I have applied this fancy formula for the standard error for the difference. And then I get a z-score, the measured value of the difference between the two proportions, minus the anticipated value if the null hypothesis were true, and the z-score is 14.5. Now, I mean, in statistics, it's unusual to see a z-score of 14.5. It means that the result is so significant, we probably didn't need to do the test. It means that the result is just very striking and could not possibly be coincidental. Normally a z-score of 2 would be impressive, and a z-score of 3 is a slam dunk. A z-score of 14.5 is just extraordinarily large. So I'm gonna, because it's off the charts in this kind of tool, I can't use this tool to calculate what happens when the z-score is 14.5. It doesn't tell us any accuracy here, but I can use this functionality, stat.norm.cdf, in order to get the p-value. And the p-value is this absurdly small number here. So what does that mean? This microscopic p-value means that, yes, we are absolutely going to reject the null hypothesis. It means the null hypothesis retains no credibility at all, and no one should seriously consider the null hypothesis. What does that mean? Well, we have to go back to the null hypothesis. The null hypothesis says blacks and whites are equally likely to die from COVID-19. And the alternative hypothesis says, no, blacks are more likely than whites to die of COVID-19. Rejection of the null hypothesis means that we have definitively demonstrated this claim that blacks are more likely than whites to die of COVID-19, at least in New York City. So this gives us a very strong conclusion here. That's what the conclusion means. It means that the mortality rate among blacks is not simply due to coincidence of sampling, but is a very real effect. It doesn't tell us what the reasons for the effect is, and we'll get into that later. But before we get into interpretations here, I'd like to talk to you about pooled estimates, which is a new concept that we haven't talked about yet and is really appropriate in this problem. So let's go back to our calculation of the standard error. And I want to criticize our calculation of the standard error. Now, why are we calculating the standard error in the first place? It's because we're trying to assess the null hypothesis. The null story says that there is going to be some random variability one way or another. And so we should expect some random variability. And our effort to calculate the standard error is our effort to account for the natural and normal variability that we will see in the difference of these two proportions, even if their actual values were equal and the difference between them was 0. So even if there were equally likely probabilities here, and even if our expectation was 0, there would be some natural variability in the difference. And that's what the standard, in the measured difference, simply due to random sampling. And that's what the standard error is trying to really express to us. Now, if so, if the null hypothesis really were true, if we really were in the null story, then P sub B and P sub W would be equal to each other, wouldn't they? And that means that it's awfully strange that we're plugging in one number for P sub B and a different number for P sub W, isn't it? It's awfully strange to plug in one thing here and another thing here, because the null story says those really ought to be the same. So what we're doing is we're breaking up our population into two different subcollections. We're breaking up the total population into the population of blacks and the population of whites, and we're measuring the fatalities among the blacks and the fatalities among the whites, and we're measuring p hat among the blacks and p hat among the whites. But if the null hypothesis is truly real here, then these ought to be the same number. So, well, they didn't work out to be the same number, but maybe that was random chance, right? So if we're really trying to assess what is the standard error, and if we really believe in the standard error as the standard error under the null story, then it doesn't really make sense to be plugging in these two different values to calculate that standard error. It should be one value. But then that raises the obvious question, which value should it be? Should it be the p hat sub B? Should it be p hat sub W? Should it be the average among them? It's not at all clear. So the value that it should be is our very best estimate for that proportion, if indeed these populations are equal. And our very best estimate for that proportion is actually this estimate. It's the total number of deaths being considered divided by the total sample size being considered. In other words, the way we should think about this is if the null hypothesis were true, then we would be assured that already that there is no difference between blacks and whites. Maybe because this hypothesis is only about blacks and whites, maybe there are differences among other populations, but we should be assured that there is no difference between blacks and whites. And so we should pool everything together. All the fatalities among black people and white people should be pooled together into a total fatality count. And the total populations of black people and white people should be pooled together to get a total population. And then the ratio between them should be calculated. That should be the value of the proportion that we should use in this calculation if we really believe that P sub B and P sub W are equal, which if we believe the null hypothesis, we do. So because we are reasoning hypothetically, because we are reasoning in terms of the null hypothesis is hypothetically assumed, what we're going to do is we're going to pool together all of the people in both of these populations. We're going to merge together all their fatalities. We're going to merge together the total counts of their populations, and we're going to calculate some overall proportion, which is an overall mortality rate in these combined populations. That's going to give us an overall value of P. And that's called the pooled estimate for P. Basically pool every case together into one big case on the grounds that the null hypothesis says they're the same anyway. And then that's our very best estimate for P. And it's a better estimate than using the estimates for P sub B and P sub W separately. So having done that, we'll get a pooled estimate for P. Now, what do we do with it? Well, we use P wherever any value of P occurs in the combined formula for the standard error. So what do we do with this P? We go back up here to this formula for the standard error, and everywhere we see a P sub B or a P sub W, we just plug in that pooled estimate P that we calculated. So let me show you how that's going to work on this tool. So we're going to calculate the pooled estimate, which is the total fatalities divided by the total sample size. And then instead of plugging in P hat B and P hat W, we're just going to plug in that pooled estimate, that thing in all of these 4 locations here. And that's going to give us the standard error. So if we rerun this using that standard error, actually we'll see a small change. Z will change from 14.57 to, we're rerunning, 15.13. So actually it's kind of ironic here. We were truly committed to reasoning hypothetically about the null hypothesis. And what that did was it slightly decreased the standard error, slightly increased the z-score, and slightly decreased the p-value, actually significantly decreased the p-value because it was already crazy small. So what's the long and the short of this? When we actually use the pooled estimate correctly here, we actually get an even slightly better result because the p-value is even slightly smaller. It doesn't really matter at this point because the p-value was already so microscopic that we rejected the null hypothesis, but it's a slightly stronger result in theory. So let's talk about interpretations. Interpretations mean, so what is the scientific conclusion? We reject the null hypothesis. Why do we reject the null hypothesis? Because, well, I didn't clarify what alpha was. Alpha was perhaps 0.05. Perhaps it was even smaller, but this p-value is going to be less than alpha for any reasonable choice of alpha. So we're going to reject the null hypothesis. What does that mean? It means P sub B is greater than P sub W. What does that mean? It means the fatality rate among blacks is significantly higher than the fatality rate among whites. And now I want to talk very carefully about what the word significant means. The word significant here is used mathematically. It's used statistically. It means that P is less than 0.05 is what it means. Significant doesn't mean big, although the numbers are big, and big would be correct to say. That's not what significant means. Significant doesn't mean important, although the numbers are important, the people are important. Significant doesn't mean important. It means not due to chance. Significant doesn't tell us whether something is blameworthy or whom to blame if it is blameworthy. If this is someone's fault, it doesn't tell us, this hypothesis test doesn't tell us whether this is someone's fault or whose fault it might be. Whenever something tragic happens, it's tempting to try to figure out whose fault it is. This hypothesis test tells us that something very real is happening, but it doesn't tell us whether it's someone's fault or whose fault it is. What it does tell us, what significant really means here is in a mathematical and statistical sense, it means not coincidental and not due to chance. It means that the observed effect is real, is not simply a little glitch in the numbers, a little bounce, a little error due to the fact that the sample size was small and we just got a little bit unlucky or something. No, it's not a coincidental thing. It tells us that the effect is real, but it doesn't tell us why. So there's a lot that this hypothesis test can't tell us, and there's a lot that we would want to know to follow up here. We would want to know, and I do want to know, it's not hypothetical, these are real numbers. We do want to know, is this due, there are lots of reasonable questions. Is this due to biological difference? It's not impossible. It seems implausible, but it's not impossible. We would want to know if it were. This doesn't tell us. Is it due to difference in treatment? Perhaps Black people are not getting the high quality treatment that white people are getting. I don't know. This significance test doesn't answer that question. Is it due to differences in exposure rates? That might seem a little implausible, but actually that's very plausible, because if you remember, essential workers have an increased exposure rate. Maybe Black New Yorkers are more likely to be essential. Maybe they're more likely to be the nurses and the grocery store clerks and et cetera, the people that we can't live without these days and who we really need to keep going to their jobs. That might lead to a difference in exposure rates. Is it somebody's fault? We can't tell. Is it due to differences in prior comorbidities? So if you're not familiar with the word comorbidity here, this is some other condition which goes along with a condition like COVID-19 that makes things even worse. So some heart problems or diabetes, for example, or hypertension or something like that, those would all be comorbidities for a COVID-19 infection if they had them. Perhaps one population or another has a different profile of common comorbidities. Or is it merely the symptom of long-term systemic inequalities? There are so many things about the differences between Black Americans and white Americans that are very real differences and are really reflections of deeper systemic inequalities. Maybe this is just another one of those. I don't know, and I can't know on the basis of this data. So I'm running statistics here, and statistics can tell us that the effect is real. It can tell us that something real is going on here, and that the people who are writing news stories about this are not just making something out of nothing, not just making mountains out of molehills. There is a real effect. That's what the statistics can tell us. But the answers to all of these deeper social questions and biological and scientific questions, this data can't tell us. These are the scientific conclusions. What about the moral conclusions? We don't know why the Black fatalities are higher, but they are, and it matters. And we need to try to learn why. Ultimately, though, it's not just a game of fairness. When it comes to pandemic, equality before death is not what we're looking for. The goal is survival. The goal is survival of everyone. So we need to fight this virus. We need to fight it with isolation, with proper manufacturing, with proper treatment, and proper vaccination when we get a chance. And we need to fight it with all of these things guided and informed by scientific leadership. We need honest, intelligent, and compassionate leaders. When we continue in the next video, we'll be discussing the chi-squared test for proportionality. And I'd like to simply preview and make one critique of this whole argument that leads to the chi-squared test of proportionality. So what we've done is we've done two small tests. One test of proportion, is this 34% significantly different from this 29? And one comparing two racial figures here. What we haven't done is assessed all 5 of these racial ethnic categories all at the same time. There's a deeper question that can be asked here and would be interesting even if these previous tests had been insignificant. The deeper question is there anywhere any significant difference on the basis of racial ethnic category? So in other words, it would be favorable here scientifically to do a test which is capable of seeking out and identifying any difference from expectation here between the population values and the actual observed fatality values. This would give us the power to say there is some racial ethnic effect, even if we didn't know exactly where to expect it. Now, this data is pretty clear, so we know where to expect it. But even if we didn't know where to expect it, it would be nice to be able to perform a statistical test that would somehow test all 5 of these categories in one go. And that's something that the chi-squared test for proportionality can do. And that's our next topic.